Hello everyone, and welcome to a new dimension for cell culture. My name is Courtney Cambaris, and I am the Business Development Manager for Solenis, and I will be presenting today's presentation. Before we get started, I would like to thank Hannah Hills from Caltag MedSystems for organizing this webinar. Caltag MedSystems is our official distributor for the UK and Ireland. I understand that we may have some attendees who are located in other countries, so please refer to our website at www.solenis.com to see a list of our international distributors. And if you're located in a country where we don't have a distributor, you can go ahead and contact us directly for your needs. Also, everyone who has joined this session today should be automatically muted. So if you notice that you're not muted, go ahead and mute yourself. And in order to participate in the live question and answer session at the end, you can answer your questions at any time using the GoToWebinar prompts on the right side of your screen, and I'll go ahead and address them at the conclusion of the webinar. Okay, so let's get started. So today I'm going to talk to you about Solenis and how we're giving a new dimension to cell culture. So the mission of Solenis is to develop innovative scaffolds for 3D cell culture. And this is to better mimic the tissue microenvironment, as well as to provide more predictive tools for drug development. I want to start with a very brief review of 2D versus 3D cell culture. So in traditional 2D cell culture, you have your growth of cells on flat plastic or glass surfaces, which is different than in a physiological 3D environment, where your cells are not grown flatly. In a traditional 2D culture, you have limited contact with the neighboring cells, whereas you have a physiological cell-cell contact in a 3D culture. You have a different exposition of nutrients, oxygen, and drugs between 2D and 3D culture. And the last point I just want to mention briefly is that co-culture of multiple cell types in 2D doesn't generally establish a microenvironment, where we can see that co-culture of multiple cell types in 3D does mimic a microenvironment. I'm going to touch on the two types of 3D technologies today, scaffold and scaffold-free. In a scaffold-free system, you have your hanging drop, for example in Sphero, your low attachment plates, and your magnetization. In these scaffold-free systems, you form your spheroids by force, so by gravity and hanging drop, by shaking, or by magnetization. And you generally have one spheroid per well. This differs from the scaffold 3D technology, and in scaffold I divided it into two sections, your synthetic scaffolds and your natural scaffolds. Your synthetic scaffolds, for example, the one from Reinnervate, which is polystyrene, it's not mimetic, it's synthetic. Whereas your natural scaffolds are more mimetic. So these include your Matrigel and your other extracellular matrix components, such as collagen gels, as well as biomimesis. The difference between these is that in a Matrigel or an extracellular matrix composition, you're going to use encapsulation to form your 3D structure, and it's difficult to control exactly what you're putting in your media. In biomimesis, we have the natural scaffold made out of hyaluronic acid, which is an extracellular matrix component. However, in this system, the cells are free to form a 3D structure because of the porosity of the scaffold. And you are also able to control your media, so you know exactly what you put inside the system. So all of the different technologies, of course, have different advantages and different disadvantages. And this is just a very brief chart of some of the disadvantages and advantages we've come up with here at Solenis. And I'm just going to briefly talk about biomimesis. So biomimesis is both easy and ready to use, which I'm going to explain in the next few slides. It's also very easy to change the media, and since it is a natural hyaluronic acid scaffold, it provides a physiologic environment. We're able to do long-term cultures in biomimesis, and we're able to retrieve our cells very easily, A, because the scaffold is porous, and B, because we can actually remove the scaffold if needed. So in the next few slides, I'm going to discuss these advantages in more detail for biomimesis. So biomimesis is a hyaluronic acid scaffold for 3D cell culture. And this is what the scaffold looks like rehydrated. It looks just like a sponge. As I said before, it's made out of hyaluronic acid. And these are the physicochemical features. So it's very porous. It's about 150 to 200 microns in pore size. And if you know a little rheology, we have an elasticity of about 500 pascals. So 500 pascals is in the soft tissue range. So for example, the liver or the intestine range. And this is the stiffness we decided to use. So this is why our stiffness is about 500 pascals. So I'm going to talk about the 3 key features of biomimesis, and then we'll go ahead and talk about some proof of concept work we've done in-house here. So this is a picture of our scaffold and 2 cells. So if you can see my pointer, here are our 2 cells kind of merging together, and all of this is the scaffold artificially stained in red. And here's a pore right here. So you can get an idea of the sizing between the cells and the pore. So it is very porous. Over here on the right-hand side, this is a spheroid of HT29 cells here, and here is the beginning of another spheroid right here, and this is our matrix, our scaffold around it. So we've seen that the biomimesis scaffold is made out of hyaluronic acid. We see that the cells grow inside the scaffold in a spheroid type structure. What I also want to point out is it's easy to use as well as being ready to use. And so we have a little video I want to show you on how you actually can use biomimesis because it illustrates it very nicely. So how to use biomimesis. It comes dehydrated in a 96 well plate. You don't have to do anything prior to use. You simply take the plate, put it in the incubator, and open it up. Then you take your media and cells and you pipette them directly on top of the scaffold. When you pipette your cells on top of the scaffold, you can go ahead and put it into the incubator at 37 degrees, as you would normally do. And what's going to happen is the scaffold's like a sponge. So it's actually going to swell up and the cells are going to go inside the scaffold. After about 48 hours, the cells should have all migrated into biomimesis, and it also becomes transparent. To change your media, you simply pipette out 100 microliters or so, and you pipette in a new 100 microliters or so. This is one of our scientists in-house doing all of our work for us. And you can see direct visualization with just a regular microscope. You don't need anything fancy. And the cells are homogeneously spread throughout the scaffold. And you really need to look at the different objectives and the different focuses because the scaffold, you're going to have cells in the z-axis as well. So you don't want to just look on the surface. You want to look inside the scaffold. So this is just a general video on how to use biomimesis and to show you that it is actually really easy to use. And then the last feature I want to mention is what it's compatible with downstream. So it's compatible with the standard analytic technologies. So the scaffold comes dehydrated, but once it's then rehydrated, it becomes transparent. So you can do microscopy. With a standard microscope, if you just want to do bright field, you can also do fluorescent microscopy. If you're interested in looking at OD or fluorescence in a plate reader, the plates are a standard 96 well plate, so they can go ahead and fit right into the plate reader. The scaffold is biodegradable. You can degrade it with hyaluronidase. So if you're interested in flow cytometry downstream, you can simply remove the scaffold and retrieve your cells and go ahead and do flow cytometry. The scaffold's also highly porous. So any kind of molecular work, protein, DNA, RNA extraction, you don't actually need to remove the scaffold. You can simply add your reagents to the cells inside the scaffold and then remove out the lysate. And lastly, if you're interested in structural type of studies, you can do histology with biomimesis as well. So you can do all the studies that you can do in 2D and biomimesis very easily. Now we're going to get into some more of the data, which is probably the more interesting part of the presentation for most of you. So here's a list of some cell lines, some primary cells, and some stem cells we've tested. We're adding to this all the time, and we have lots of people testing it, so this list is certainly not complete, but it'll give you a nice overview. Most of the cell lines we've tested have been cancer cell lines, breast, colorectal, lung, pancreas. We've tested human white preadipocytes, as well as human hepatocytes, cryopreserved for primary cells. And we've tested four different types of stem cells: the hematopoietic, the human-induced pluripotent stem cells, as well as human and mouse embryonic stem cells. What's nice with stem cells is since the media change is so easy to do, you can do your differentiation fairly easily. What I want to show you over here is just the different three-dimensional structures we see, because they're not the same. It varies by cell type. So these two are our PANC1 or HT29 cell lines, and you can see that they form nice spheroids. Here is the hematopoietic stem cells, and you can see that it forms more of a great cluster. Over here we have our matured adipocytes, which is more of an aggregate, and you can see they're big, fat, round cells full of fat. Right here we have our fibroblasts, which is completely different than 2D. In 2D they're flat. We actually have like a spheroid-looking fibroblast. And then lastly over here is our mouse embryonic stem cell spheroid that we see. So if we're going to move on to looking at the spheroid viability and growth. So these are HT29 cells at day 28 using a live dead kit. And the first thing I want to mention is that it's multispheroid. So you see we have lots of spheroids inside of our scaffold. At day 28 using the live dead test, you can see that maybe you can see one or two little red dots, but the vast majority of them are all living and healthy. And you can see that the size of the cells is really increasing with time while it's remaining viable. So for HT29 cells, for example, at day 7, they're between 50 and 100. By day 14, they're between 100 to 150. And by day 28, they're between 150 to 200. Now remember that the size of the spheroid really depends on the cell type. So this is true for HT29 cells. It may not be true for hepatocytes, for example. So let's go into more detail using immunocytochemistry. So we decided to look at the cytoskeleton organization. So we looked at tubulin in red and actin in green. And you can see in 2D, you see tubulin expression around every single cell. Whereas in 3D, we see that the tubulin is localized at the spheroid periphery, which is very different. And we know that it's not a penetration issue because we've tried several different markers and we've never noticed an issue with penetration into the spheroid. We wanted to look deeper into this, and so we went ahead and we extracted protein and RNA. And you can see that we have less tubulin in 3D at day 7 than we have in 2D. However, if you look at the gene analysis, we have about the same level. We have a similar level. So this indicates to us that it's a translational question, not a transcriptional question. And the point of this isn't to study tubulin, but it's to demonstrate that you can do these types of experiments as you would do in 2D, which can be really difficult to do in other 3D technologies. If you want to look at more markers, as I said before, you can digest the scaffold using hyaluronidase, and then you can disaggregate the spheroids with detachant and use those single cells for flow cytometry. So here, for example, we studied the proliferation rate, and we see that the proliferation rate in 3D is slower than it is in 2D, and this is because they're forming 3D structures. They're not just growing flat on a dish. So now we've seen that the cytoskeleton is different, that protein and RNA expression can differ, and that the proliferation rate differs in 2D versus 3D. So what comes next? So we decided to look at the extracellular matrix secretion. So in 2D cells, they don't really produce their own microenvironment. Whereas in 3D cells, we can actually see that the cells are producing their own microenvironment. We can see that they're producing collagen 1 in both HT29, HepG2, as well as HeLa cells, where you don't see so much in the 2D. And of course, if you want to test for drug discovery capabilities, you can certainly do that. You can simply add the drugs right into the media and or just into the well, depending on how you want to do it. And if we look at what we see here, so we looked at 5-fluorouracil using HT29 or DLD1 cells. And you can see this graph on the right that in 3D, you need a much greater amount of drug than you would need in 2D. And this is because you have a more physiological condition. The IC50 is shifted because it's going to take more drug to penetrate through the spheroid. And I think this is illustrated really beautifully if you look over here at this picture. So here's our HT29 cells with no drug. And here's our H229 cells with 10 micromolars of 5-FU for 72 hours. And you can see that you have a few dead cells here in the middle. But then if you look at 250 micromolar of drug after 72 hours, basically you've exploded your spheroid and you've killed your cells. So this shows us that 3D cell culture and biomimesis really is a predictive tool for drug discovery, and it makes a nice bridge between your 2D IC50s and then your in vivo animal testing. It's a nice bridge between the two of them. So I've told you a little bit about biomimesis, our hyaluronic acid scaffold, and I wanted to give you a little idea of where the company is moving in the future. So we've developed 2 functionalized scaffolds currently, one for adipocytes as well as one for hepatocytes. And I wanted to give you a little teaser of both of them. So we based our scaffold for adipocytes on the literature. And then, so it is made out of hyaluronic acid plus collagen 1 and collagen 6. The collagens are stained artificially. And we based it off of the information in the literature. However, you can see that it looks very, very similar to in vivo decellularized human adipose tissue, which was the goal. The physicochemical properties are very similar to what you saw in the biomimesis hyaluronic acid scaffold. This also has, I'm sorry, I forgot to mention, this also has fibronectin motifs as well as the collagen 1 and 6. In terms of, do the cells like it? How do they grow in it? This is your adipose tissue from human abdomen liposuction. You can see that they're all round cells clustered together in vivo. And here is looking at what the adipocytes look like. These are murine pre-adipocyte cell line at day 7. And this is your human white pre-adipocytes at day 14. And you can see that they form a nice cluster. You can see that the cells are fairly big. And we see that the in vivo organization of adipose tissue looks very similar to what we see in the biomimesis adipocyte. In addition to this, which I'm not going to show today, we've also done lipolysis and lipogenesis studies in this scaffold. So we know that these cells are metabolically active as well as healthy and viable cells. And then I'm just going to tell you a couple slides on the biomimesis hepatocyte. So similarly to the biomimesis adipocyte, we based our scaffold structure on the literature. This is a hyaluronic acid with collagen 1 and collagen 4, along with fibronectin motifs and galactose. And over here you see the in vivo decellularized hepatic extracellular matrix, and you can see how similar they look again. The physicochemical features are the same as you would see with the biomimesis adipocyte and biomimesis hyaluronic acid. In terms of what we've done downstream, we've done lots of things downstream, but I don't have time to talk about it all. So we've done HepG2 and human hepatocytes cryopreserved. This is looking at live dead testing. This is after 28 days, and this is after 14 days with human hepatocytes. So we can keep these cells in culture long term, which is very unusual, and it's something that's really hard to do in 2D. So we know the cells are alive. So one of the next things we wanted to test is we wanted to say, okay, well, they're alive. Are they actually metabolically active? So we checked for activity by looking at the basal and induced activity of the CEAP1 gene. So we see the basal activity between a 2D, which is a collagen 1 sandwich, and the 3D in biomimesis. We have 3 times increase in basal activity. And then we wanted to look at induced activity. So we used minoprezol for our inducer, and we can see that there's a 19 times higher induced activity in biomimesis 3D than we see in our basal activity. So we know that in 3D culture in biomimesis hepatocyte, you can see healthy and metabolically competent human hepatocytes cultured for at least 2 weeks. And this really allows drug screening possibilities and long-term studies. So how do they come? So right now, they're in a 96-well low attachment plate format from Greiner. And what we do is we can fill this 96-well plate either completely full with 96 hydrogels. We can fill it halfway full with 48 hydrogels, or we can put 24 hydrogels in. And it's the exact same. We have it in black as well too, if you're interested in fluorescent studies. We saw a cell retrieval kit for digesting the Biomimesis hyaluronic acid scaffold. The plates are barcoded. This is for our quality assurance on our end. It's also if you're interested in using robotics, you can go ahead and have them scan through with the robot. And currently they are research use only. So just to reiterate and kind of give you our take-home points, Biomimesis is a physiological scaffold. So it's mimicking the cell's microenvironment. It's made out of an extracellular matrix component. It's easy and ready to use, as you saw in the video, and it's compatible with all your downstream analytical technologies. So any kind of downstream work you want to do, you can do with this scaffold. Now I'm going to go ahead and answer some questions. I want to leave up the contact information. So we have lots more studies that we've done with adipocytes and hepatocytes as well as Biomimesis. And we update our website very frequently, and this is where we put our newest stuff. So I'd really encourage you to visit our website at www.solenis.com for any latest news and products. If you want to speak directly with us, technical support, you can contact my colleague, Christophe Petrel, and this is his phone number and email. And of course, you're always welcome to contact our distributor. Hannah's a wonderful person at Caltag Med Systems, and they can help answer any questions you have about shipping, ordering, pricing. Okay, so I'm going to go ahead and see what kind of questions we have. Okay. So we have a question about, is it simple to do confocal microscopy with Biomimesis? The answer to that is yes. So Biomimesis is transparent and porous. You can do it easily directly inside the well with about the same protocol you use in 2D. You can do it directly inside the plate. You can also do it in a black plate with a glass bottom, or you can actually take the hydrogel out of the well using a pair of forceps, and you can put it right on a glass slide. We do have a 3D reconstruction of a spheroid done with a light sheet microscope. Another question we have is, can we do co-culture in Biomimesis? And the answer to that is absolutely. So far in-house, we've tried to mimic the tumor environment using cancer cell lines and cancer-associated fibroblasts plus blood endothelial cells, CUVEX, to mimic angiogenesis, and we've had some nice results on this. What the most important thing to do with co-culture is to set up the ratio of cell-to-cell quantity. And we have customers doing this with lots of different cells right now as well. We got a question about, can Biomimesis be used for whole small tissue biopsies? So yes, the biopsy has to be digested to enter into the hydrogel. So the pore size of the hydrogel is about 150 to 200. So it depends how big the biopsy is. The smallest possible starting number of cells that we use is 50,000. So we seed our scaffolds with around 50,000 cells per scaffold and about 20 to 30 microliters of media. And then you top it off with another 175 to 180 microliters. Let me see if we have any more questions. Looks like we just have one more. I just want to mention with that you can use less cells as well. Depending on your cell type, you have to optimize how many cells. We recommend beginning with about 50,000 cells per hydrogel, and then you can scale up and down from there. And then we had one question about customizing scaffolds. So this is service. So we do this on a case-by-case basis with our R&D chemistry department about the stiffness of the scaffold or what you want grafted into the scaffold, and it really depends on the feasibility with the hyaluronic acid chemistry. So it is something we can do. It's something we would need to discuss one-on-one. And I think that is about it for the questions. I don't see any more. If you have any questions, please don't hesitate to send us an email. Oh wait, no, I see some more. So what is the thickness of the scaffold? The scaffold is about 2 millimeters thick. And the maximal cell density you can use, I'm not actually sure what the maximal is, maybe 100,000-ish. I have people using about 75,000 with stem cells, and they have not reached confluency. Perhaps you can even use up to 1 million. Not quite sure. It's something that would have to be tested. The depth of the hydrogel in each well, they're about 2 millimeters in height. So the addition of collagen in the biomimesis adipocyte and hepatocyte does not affect transparency. You can still see through the scaffold. That's not an issue. Validation-wise, with high content screening, we have some people working on that currently. We should have some results from them soon. We're working on 2 new formats. So we're making right now a 24 well format plate and a 384 well format plate, and that should be ready soon. And we'll probably do some validation studies once we have that in there. And let me see if I have any more. So I think I have a couple questions that are very specific, so I'll go ahead and send you an email at the end if I didn't have a chance to get to your question, because I don't have enough time today to explain everything. But if you have further follow-up questions, please feel free to contact Christophe or Hannah with your further questions, and we'll get back to you as soon as possible. Okay. Thank you very much for attending the webinar. I appreciate it, and hopefully we will hear from you soon. Bye-bye.